This video is going to look at how to get displacement or position from velocity, either in an equation form or a plot form. Now, because of these two forms that we're going to be working with, this relates to two major learning outcomes for the class: the representation side of working with plots, and then the problem-solving side of actually needing to do out some math, both algebra-based math and some calculus-based math as well. So, to start with, let's think of what's going on graphically. So if we have a velocity that is changing with time, we need to think about how to get displacement from that. Now, before we said in the case where we had a constant velocity that our displacement, so change in position, I'm using S as my general coordinate, is equal to my velocity in that direction times the elapsed time. But this only works if your velocity here is constant. So in the case where we have a changing velocity, like this plot here shows, we can't really do this since we don't have one value to use. But what you can imagine doing is basically breaking this plot up into little chunks that approximates this shape. Now this is again mostly a thought experiment. This isn't something you will literally be doing every time or something we would be mathematically doing, but it's to help us get there logically. And what you note is once you break it up into this sort of stair-step pattern, now for at least this little time window, we have one value of v. So we could find what this displacement is by multiplying the delta t, your time window, by this value for v. And that's actually equivalent to finding the area of this rectangle. So what this thought process hopefully gets you to is, as we're finding all of these rectangles, they would actually sum up, as you think about different little time windows, to be the area under the curve. So if we in fact are taking our delta t and making it a derivative, dt, now you're just doing your integral and you're getting the entire area under the curve. So to get our change in position or our displacement for a continuously varying velocity like this, you actually need to do an integral. Now, one thing to think about, that when we do have a plot like this where it's changing, we could talk about an average velocity, just as you can take an average of any function. But what we're really thinking about in this case is an instantaneous velocity, where we have a different velocity defined for every single moment in time. So if the idea of an instantaneous velocity is new to you, you probably want to search out those videos that describe that and watch those first before moving on here. So now what we're going to do is think a little bit about how this is going to work mathematically, not just in plots. So we said that velocity was our time derivative of position. So if we want to get position, or specifically displacement from velocity, we go backwards. So in this direction we were taking the derivative, so going backwards is going to be doing the integral. So to get our change in position between two times, initial and final time, we would integrate our velocity over that time window, and that gives us again our change in position. Now if we have a very specific function of what our velocity looks like as a function of time, we then just integrate that function. And now one thing here that I'm trying to denote with my notation that may or may not be very clear is that if what you want is a position as a function of time, and you have some initial position and some initial time, well then you are just integrating this, where this upper limit of your integral is just t, where that's variable t. So mathematically, what's inside our integral here technically shouldn't look the same as the bounds of our integral here. Now frequently this is just going to be 0, so that's not too bad, and this ends up just looking then as the indefinite integral rather than the definite integral. So that's one thing to just think about, that we can integrate our functional form of velocity to get the functional form of position, but we must always add on that initial position. So anytime that you have a plot of velocity, or it's been described to you what velocity is doing as a function of time, that doesn't tell you anything about your initial position. Now normally we're going to define our initial position to be 0. That's just very convenient. And that's like talking about the starting line of a race, that is typically going to be 0. But what you need to be careful about here is if you have 2 people starting a race where they're not starting in the same position, only one of them can really be starting at 0. You need to define the other to actually have an initial position. So do be careful about this, and remember that anytime you're integrating, there was that constant of integration when you're doing the indefinite integral, and that's equal to just this initial position. That's what we have here.